Hello and welcome to the second part of the design of foot over bridge. So in the first part we have already seen the step number 1 to step number 8. So in the second part we will see from the step number 9 to step number 15. So in this video we will see the forces in vertical member, forces in diagonal member, design of bottom chord member, top chord member, vertical member and diagonal member, and lastly we will see the design of particular joint. So this was the particular question which we have solved in the part 1 up to step number 8, and from this we will start with the step number 9. So the step number 9 is force in the vertical member. So coming on to the vertical member, the particular vertical member, here you can see this is the vertical member. Here these are known as the vertical member. So we have to design as well as we have to calculate, we have to know the force in this particular member. So let us start with the step number 9, forces in the vertical member. Similarly, we have already seen the U, which means the upper, and L, which means the lower. So this will be the this point is known as U0 and this point is known as L0. So what we have to do, we have to find the force in the member, or we can say vertical member U0, U1, and we will consider positive value as the compression and negative value as the tension. Now we have to plot the IDL for the vertical member U0, L0. Now what we will do, we will plot one triangle, and in which we will find the height. So in the vertical member we will not find the height by using that particular HT equation. We will find the height by using, if there is 8 number of panel, we have already seen that in the particular truss there is 8 number of panel, each panel is of 3 meter, so the total length will be 24 meter. So here you can see there will be one panel, and here it will be remaining 8 minus 1, which will be 7 panel. So we will calculate height of this particular ideal as 7, which will be the number of panel on the right hand side, divide by total number of panel, which is total number of panel is 8. So we will have the height of that particular ideal as 0.875. okay, now what we will do, we will find the particular force in the particular member U0, L0. So the formula will be area of ideal into total UDL, which we have calculated in this step number 5 in the part 1. So the force in the particular member U0, L0 will be 279.3 kilonewton, which is in positive, so it will be as the compression force. Now coming on to the second vertical member, which is U1, L1. So in this here we have to plot, similarly we have to plot the ideal diagram for the particular member, vertical member U1, L1. So here we have to calculate the two different heights, which will be one in the compression and second it will be in the tension. So so let us see for the positive triangle. So in this particular positive triangle, here you can see there are number of panel will be 1, 2, 3, 4, 5 and 6. So the panel will be 6, and here it will be particular panel 1, so it will be 1A. Now if we see, then we will see the height. So if we see for this positive ideal diagram, the height will be number of panel, which is 6, divide by total number of panel, which will be 8. So we have got the height for the positive ideal as 0.75. Coming on to the negative side, so the number of panel is 1, divide by total number of panel is 8. So the height for the negative ideal will be 0.125. Now what we will do, we will find the value of x. as we know, the width of this particular panel is 3 meter. So if we consider this value as a x, then this value will be 3 minus x. So we will find the value of x. So x upon 0.125 is equals to 3 minus x upon 0.75. So we will get the value of x as 0.428 meters, and the value of this particular thing will be 3 minus 0.428. Now let us find the forces. So the force P U1 L1 is equals to area of ideal. Now in this case, the area of ideal will be, there are two areas. One will be positive area and the second will be negative area. So first let us see positive area, which means this triangle. We will see this triangle. So for this triangle, the area will be half into base. So in our case, half 0.5 into height 0.75 into base. So the base will be from this to this, which will be 24 overall, 24 minus this distance. So which will be 24 minus this panel, which is of 3 meters, and distance x, which is 0.428. So 24 minus 3 minus 0.428. Now coming on to the second area, which will be in the negative side. So we will see this part, this triangle. So it will be half into height, which will be 0.125 into the base. So the base will be 1a. So value of a is 3. So 3 plus x. So 0.428. So it will be 3 plus 0.428. Now what we will do is, we will have the solution for this particular positive side. So it is 7.714, and the answer for the negative area will be 0.21. So we will by deducting this thing, we have found the net area as 7.5 meter square. Now what we will do is, so the factored force due to live load or factor force due to dead load will be total area, net area, into the dead load, which is 11.6, which we have already seen in the step number 5. So the factored force due to dead load will be 87 kilonewton. And moving on to the live load, so force due to live load, in live load there will be two different live load, because there is positive value as well as there is negative value. So let us first see for the compression, which means for the positive value. So in our case, the positive area is 7.714. So there will be area 7.714 into live load, which we have already seen in the step number 5, which is 15. So we will get the force due to live load due to in compression. It will be 115.65 kilonewton. Similarly, force due to live load in tension. So tension means negative area. So in our case, the negative area is 0.21 into the live load 15, which we already seen in the step number 5. So the force due to live load in tension will be minus 3.15 kilonewton. Now what we will do, we will do the load combination. So for load combination, what we have to do? We have to do is dead load plus live load in compression, and second dead load plus live load in tension. So dead load, so we have already calculated that dead load as 87 kilonewton plus live load in compression. So live load in compression is 115.65. So we'll have the combination of dead load plus live load in compression as 202.65 kilonewton, which is compression. And similarly, coming on to the dead load plus live load in tension, so the dead load is 87.0 kilonewton, and the live load due to tension is minus 3.15. So we have the value as 83.85 kilonewton as a compression. So we have seen the force in the vertical member U1 L1 as 202.65 kilonewton, which is maximum, which can be used for the design of that particular member. Similarly, moving on to the vertical member U2L2, which will be similarly as we have seen for the member L1 L2 in the previous slide. So in this we have found the load combination for dead load live load compression as 132.55 and dead load live load combination for the tension as 339.34. So from this we will use maximum for the design purpose. Similarly, moving on to the member U3L3, it will be similar as we have seen in the vertical member U1L1. So in this case we have the load combinations as 63.85 kilonewton as a compression and second load combination as 11.55 kilonewton, which is in the tension. And we will move for the center part only. So as we know, the value of right hand side which will be equal to the left hand side. Now step number 10, forces in diagonal member. So for the forces in diagonal member, so here you can see the diagonal member is U0 L1, then U1 L2, U3 L3, and lastly U3 L4. These are the diagonal members. So if we see the particular thing, then the forces in the diagonal member will be negative force in vertical member into 1 upon sine 45. 1 upon sine 45, because this the diagonal member will be at an angle of 45 degree. So we have to multiply for calculating the force in diagonal member, we have to multiply the negative force in the vertical member into 1.41. So first let us see this table. So what we have to do is make a table in which there is a vertical member and there is a force in vertical member, maximum and minimum forces. Now we have seen vertical member as U0 L0, U1 L1, U2 L2 and U3 L3. Let us see. So in the vertical force, or we can say in the vertical member U0 L0, the force we have obtained is 279.3 kilonewton as positive. So what we have we will do is we will make the maximum value U0 L0 as 279.3 kilonewton as a compression. So moving on to the L1 U1 L1. So let us see in U1 L1. So in the particular member U1 L1, the force we have obtained is 202 as a maximum and minimum as 83. So we will write that particular force 202 in maximum and 83 as in the minimum. Similarly, coming on to the U2 L2. So in the particular member U2 L2, we have the maximum force as 132 and minimum as 39. So we will write maximum as 132.6 and minimum as 39. Coming on to the vertical member U3 L3. So in the particular member U3 L3, the maximum is 63.85 kilonewton and minimum is 11.55. So we will write 68.85 and negative 11.5. Now what we will do, we will just put the values in this particular formula, and we will make a similar table for diagonal member. So just write diagonal member and its diagonal particular member U0 L1, U1 L2, U2 L3 and U3 L4. So we have written something like this. And now what we will do, for the particular U0 L1, we will find the force in diagonal member as this formula. Let us clean. So For this value negative 394.98, what we'll do is negative of the vertical force into 1.41, so we'll get the value as negative 394.98. Similarly, coming on to the diagonal member U1 L2, the force will be, the maximum force will be the maximum force in the vertical member into the 1.41, so we'll obtain negative 286.5. Similarly, force in the minimum force in the vertical member into the 1.14, so we'll get as 118.5 kilonewton. Similarly, we have to calculate the diagonal member forces maximum as well as minimum in U2L3 and U3L4. Now moving on to the design force. So we have already seen the forces in the top chord member, bottom chord member, diagonal member and vertical member. So in top chord member, the particular member which has the maximum load, we have to consider that. So in the top chord member, we have obtained the maximum force as 638.4 kilonewton as a compression. In bottom chord member, we have obtained negative 598.5 kilonewton as a maximum tension force. In vertical member, we have got two forces. One is compressive force and the tension force. So the maximum compressive force is 279.3 kilonewton and the maximum tension force is minus 11.55 kilo Newton. Coming on to the diagonal member, so the maximum tension force is negative 395 kilonewton and the positive compression force is maximum 16.33. So this force will be used for the design of the particular compression or tension member. So in this question, we will design one tension member which will be the bottom chord and one compression member which will be the vertical. Rest of will be same. So for tension member, we will design for the bottom chord member, in which the force we will use will be negative 598.5 kilonewton, and for the compression member we will design the vertical member, in which we will use the force as 279.3 kilonewton. So let us start with the step number 11, which is the design for bottom chord member. So we have the design load as 598.5 kilonewton and the Fy is 250. So we will find Ag, and we will find Ag by using IS 800 2007, which is given in page number 32. So we have obtained the area as 2633.4 mm square. So we will provide 2 ISA. So by providing 2 ISA, we have to divide the area by 2. So we have the area, gross area, as 1316.4 mm square. So I have selected 2 ISA 125, 75, 8 mm on the both side using a gusset plate with longer edge is kept horizontal. So now go to the IS 800 page number 32. From that we have to calculate the strength governed due to strength governed by yielding of gross section, and design of strength due to rupture of critical section, and design of strength due to block shear. These all formulas are provided in page number 32. So I have obtained the particular strength governed due to yielding of gross section as 699.09, which is greater than the design load, which means it is safer. And coming on to the second step, which is design strength due to rupture of critical section. So we have obtained it as 713.73, which is greater than the design load, which is safer, and it is okay. And coming on to the third, which is design strength due to block shear, which we have obtained as 664.74, which is greater than the design load, which is safer and it is okay. So hence we have provided the 2 ISA 125 cross 75 cross 8 mm for the bottom chord member. So similarly, coming on to the design of the vertical member, so the vertical member which will be designed as the design of compression member. So the design load we have is 279.3 kilonewton and Fy is 250. We will assume the slenderness ratio as 120. So we will have the KL by R ratio as 120. So FCD is equals to 83.7 MPa, which we have got from page number 42 of IS 800 2007. So area required will be force upon FCD. So we already have the force design load as 279.3 kilonewton. We have to convert into Newton and divide by FCD. So in our case the FCD is 83.7. So we have got the area required as 3337 mm square. So let us try 2 ISA 90 cross 90 cross 10 mm on the both side of the GP with longer leg is kept horizontal. So our area will be something 3406 mm square. We have provided 2 ISA, so it will be divided by 2, and hence it is greater than the area required, which is okay, and it is a sign of the safer side. And the R value of R minimum, which will be which we can have from the code, which is 27.3 mm. Now we will find KL by R ratio. So in our case the KL by R ratio we have obtained as 93.4, and lastly we will find the value of FCK as per the new KL by R ratio. So we will have the value of FCD as 116.24 Newton per mm square from IS 800 page number 42 table number 9C. So we will have the compressive force PD as area into FCD. So the area will be new area which we have obtained by using 2 ISA 90 cross 90 cross 10 into we will have the new FCD which we have calculated as per the new KL by R ratio. So we will have the compressive force as 395.91 kilonewton, which is greater than the design load. So it is okay and safer against it. So we can provide 2 ISA 90 cross 90 cross 10 mm on the both side of the GP. Now similarly you can design the for the top chord member, in which after designing you may get the answer as 2 ISA 150 cross 115 cross 12 mm, and in which the design force you will obtain as 901.6, which will be greater than the design force, which will be safer against it. And you can also design the particular diagonal member, in which I have got the I have provided 2 ISA 80 cross 80 cross 6 mm, and it is safer against the particular design load. Now coming on to the last step, which is step number 15, design of particular joint. So I have taken particular joint as U0. I have shown only one joint. You can further go through different joints. So the main formula for calculating the number of bolts required at particular joint will be force upon double shear. So the value of double shear will be 90.6. Now let us see if we have to design the number of bolts for the particular joint U0. You need the force in the particular member U0L1, then U0L0, and you need the force in the member U0L3. So let us see. So the number of bolts required at joint U0L1, U0U1. So U0U1, for U0U1. So the force in this particular member we have is 279.3 kilonewton divided by double shear, which is 90.6. So we got 4 numbers of bolt. So we will provide 4 numbers of bolt connecting GP. Now Similarly, coming on to the U0 L0. So for U0 L0, number of bolts required for U0 L0 will be force in this particular member U0 L0 divided by double shear. So we will have obtained the particular number as 4 number of the bolts over here. Now coming on to the member U0 L1, the number of bolts required for U0 L1 will be force in this particular member divided by double shear. So we have got the number of bolts as 5. So we have provided 5 number of bolts connecting GP. So this was the design for the joint. You can also try for different joints. So here we have successfully completed with the design of the particular foot over bridge, which has been divided into 2 parts. Thanks for watching. If there is any query related to the design of tension member as well as design for the compression member, you can comment me, and thanks for watching.